Today we're going to write exponential functions from tables, and you can use a date of June 9th. Your note packet should have 3 pages. So in the last few lessons, we've been examining exponential functions. Most exponential functions take this form. We have A, which represents our initial amount, and B, which is our growth or decay factor. And then we know that it's exponential because it's raised to the x power. Here's an example. If you'll take a minute and put this into your iPad. Now that it's in your iPad, we want to create a table of values over the interval from 0 to 5 inclusive. So you can activate the split screen table on your iPad, and these are the values that you should see. So the first question says, is this growth or decay? If you examine the table, we started at 3.7, and you can see that we're increasing our numbers. So this has to be a growth function. So then what is the growth factor? Well, the growth factor is present in the function itself. The value of b, which is 2, represents our growth factor. So we're multiplying each value by 2. The initial amount is when x equals 0. In our table, we can see that it was 3.7. The initial amount is also present in the original function. Right here, a is 3.7. So in order to write an exponential function, we need to know the initial amount a and the growth factor b. And sometimes we refer to b as r, which is our common ratio. So with example number 2, we're going to write an exponential function from this table of values. And we want it to be in this format. So the first thing we want is the initial amount. On the table, we can see that when x equals 0, y is 81. So that is our starting amount. And then we need to calculate b, our growth or decay factor. In my table, I can see that the values are decreasing. So this is going to be a decay model. But I'm going to calculate r. You can pick any term and then divide it by the term that came just prior. So if I reduce this, my common ratio is 1/3, which does model decay. So with those two pieces known, we can write our exponential function. So it'll be y equals 81, my initial amount, times 1/3 to the x power. We're going to do the same thing in number 3. We want it to have this format. Do we have a, the initial amount when x equals 0? In this particular table, that is not provided. So we're not going to start with a. We're going to start with b or r, our growth or decay factor. So you can see in the table that our numbers are getting bigger. So this is a growth model. You can pick any value of y to start with. I'm selecting 29.04, and I'm dividing by the number just previous. So this tells me that my growth rate is 2.2. Now that I know the growth rate, I can actually calculate the value when x equals 0. We're going to take 13.2 and divide it by 2.2. And now I know that my initial amount a is 6. So we can put it all together. And our function, 6 times 2.2 to the x power. In example number 4, we have data provided from a largemouth bass population in a local pond. We need to find the exponential function that models this situation. They're telling us to let 0 represent 1970. 1970 is the base year where they took the initial reading of bass in the pond. We are going to represent that with 0. So this is really x equals 0. Each year then will be 1. But they're skipping 1971, so 1972 is actually year 2. And then all these years that follow are really the last digit, 3 through 8. Now, I did fill in the value for 0, but I did have to calculate that value first. So I need to know what the growth rate is. I did start with 322 and divide it by 200. So I know that my bass population is growing by a rate of 1.61 per year. I'm going to use this value to work backwards and find the number of bass in the pond in 1971. So I'm going to take 200 and divide it by 1.61. I did round the answer off to 124. The decimal was 0.22. And now that I know the bass population in 1971, I can again work backward and divide 124 by 1.61 to find the bass population in 1970. And again, I rounded the 77, but that makes sense in the context of the problem. We don't have half of a fish. So the value of y for 1970 is filled in as 77 bass. So now I do have an initial amount of 77, and I have a growth rate of 1.61, and my function is here. In number 5, we're actually going to use the graph to write the exponential function. We still need the same information. So we're looking for when x equals 0. So on the x-axis, right here is 0. This value where the graph crosses is 1 because they're counting in blocks of 2. Now we also have to calculate our common ratio. This is definitely a growth model because I can see it increasing over time. You can pick any values, any of these purple dots that you want. What I did is I've selected when x equals 3, the y value is 8. And then the term prior, when x equals 2, y is 4. So 8 divided by 4 gives me a growth rate of 2. We're multiplying by 2. So my function can be 1 times 2 to the x power, but we can also choose to eliminate a as 1. And this is our parent function for an exponential growth model. This is going to be homework number 128. You can cross off number 7. That's a little more challenging than I want it to be. But you're going to write exponential functions for 1 through 6, and then you're going to state domain and range. 4, 5, and 6 down here, they're asking you to calculate the rate of change. This is the interval. So you'll need the ordered pair at 0 and the ordered pair at 1. Same thing at 2 and 3. So you want to state the ordered pairs and then calculate your average rate of change. If you have any questions as you go through the notes or the assignment, please let me know. Have a great day.